Professor Park will tell us about Pseudogap in cerium-based heavy fermion superconductors. And we're seeing your desktop. That looks great. And please take it away.
All right. Okay, so thank you, Chairman, for the introduction, and I'd like to thank organizers, especially Chimao, for inviting me to this workshop. And so in this talk, my main message is there is a pseudogap, which is different from what has been reported in other strongly correlated superconductors. So, and in cerium-based heavy fermion superconductors. Oops. Okay, and then most of the work that I present today has been performed by Harim and Brong, and that Harim is now in University Hamburg as a postdoctor, and this work has been done in collaboration with Professor Shin Nu from Zhejiang University. Okay, so okay, somehow let's see. Okay. Pseudogap in conventional superconductors has attracted a great interest because of its potential connection with high temperature superconductivity. And then these figures, some examples are high-tissue cuprate and iron-based nuclide, where this T-star line, which signifies the onset of pseudogap state, has been very actively studied in both types of families of superconductors, suggesting that the pseudogap could be an ubiquitous phase in conventional superconductors. How about the cerium-based heavy fermion superconductors? The figure on the left is the temperature pressure phase diagram of both cerium indium-3 and cerium rhodium indium-5. And then pseudogap-like the behavior has been also reported, like in cerium rhodium indium-5, like as here is a T-star. And then the still in very hardly debated is that its origin. Is it really due to the preformed Cooper pairs, or is it due to other competing interactions? So this is the middle panel, the small. I hope that you can see it. Is the temperature phase diagram of cerium cobalt indium-5, where the dome of conductivity here is maximized, is around 1.5 GPa. At low pressure range below 1.5 GPa, as shown here in figure left, the electrical resistivity shows deviation from the T linear dependence below this T so-called pseudogap, which is slightly higher than temperature. And then at temperature higher than this optimal pressure, then as you can see, there is a deviation from the normal state line showing a T-square dependence, and we call it Fermi liquid state. So, and then the low pressure, high pressure side deviation from the normal state has been associated with appearance of Fermi liquid, while a low pressure side is connected with pseudogap. And then evidence for pseudogap state has been also reported in STM by Ali Yazdani's group. And this is the conductance as a function of biased voltage. And then here, at very low temperature, this the blue line is at temperature around 245 millikelvin. And as you can see, there is a very sharp dip around the zero bias energy, which is due to the superconducting gap. And then with the increasing pressure, then the gap, this shaft feature becomes lower and lower. And then the highlighted by yellow is a temperature around 5.3 Kelvin. And as you can see, even though the temperature is higher than TC, you can still see a dip in the conductance due to the depletion in the density state, and they assigned this as pseudogap. And then this is feature as a on the magnetic field at 245 millikelvin. The pseudogap, the superconducting gap is very sharp, and at around 5.7 Tesla, it's all gone, and still there is a dip-like feature, and then which is consistent with a pseudogap in cerium cobalt indium 5. Another evidence comes from the planar tunneling spectroscopy by Laura Green's group, and then this is conductance curve as a function of sample bias, and there is a U shape due to superconducting gap, and then it becomes shallow and around 2 Kelvin. And the TC, as you know, is around 2.3 Kelvin. At 2.5 Kelvin, this feature still survives and very clear, and almost all the way to 4 Kelvin, very clear a dip-like feature. And when plotted, the size of the gap as a function of temperature, which is these blue symbols, this does not end at TC, but rather is persistent all the way to 5 Kelvin. And then this smooth evolution from low temperature across the TC, they associate this feature as an evidence for preformed Cooper pairs. And this is the temperature and doping phase diagram of the cerium cobalt indium 5. And the left side is cadmium doping, namely the hole doping. The right side is tin doping, named electron doping. And this is coherence temperature, which evolves smoothly. And then this dome of superconductivity surrounding the zero doping. And then, as you can see, that this is only one data point, and which suggests that in order to clarify the origin of the pseudogap phase, I think we need more work. And this is and the story suggested the various types of phase diagram that are different from its origin. And then this is temperature and control parameter phase diagram for the scenario of preformed Cooper pairs. And then in this scenario, the T-star line is persistent and then end at the point where the superconductivity disappears. On the other hand, if the pseudogap is due to competing order, then the pseudogap line ends inside the dome. And the third scenario, which is much more complicated, is the combination of both preformed Cooper pair and competing order. So meaning that the preformed Cooper pairs and then additional competing interactions are around. Then this pseudogap-like feature, it's not gradual, but rather shows very complicated behavior like this type of. So in order to study the pseudogap-like behavior in the cerium-based compound, we studied so-called point contact spectroscopy, which can directly study the superconducting gap behavior, which this technique, as you well aware, take advantage of so-called endraft reflection spectroscopy, where the electrons from the normal metal incident on a superconductor and then is retroreflected as a whole, thus producing the Cooper pair. Because of this, the differential conductance as a function of this biased voltage or biased energy, then the conductance in the normal state is 1, and then within the gap this becomes doubled because of the newly generated the Cooper pairs. And here Z is the barrier strength, and then with the increasing the barrier, the interface barrier, as you can see that this type U-shaped behavior becomes more and more clear, and around Z equal 1, then looks like the tunneling experiment. So in order to apply this point contact spectroscopy on the extreme conditions, especially on the pressure, that we use different techniques. Like, for example, at pressures below 2.5 GPa, that we use so-called soft point contact spectroscopy, and where the silver solution was used, and these silver nanoparticles, small silver particles provide the contact junctions that needed for spectroscopy. And then we use the piston type cylinder cell. And at pressures up to megabar range, then we use so-called diamond anvil pressure cell here. And then the contact was provided by the platinum wire, and where the end becomes very sharp. So this is the representative data of the diffraction conductance as a function of a bias voltage, and then this is at ambient pressure and 1.5 Kelvin, and as you can see that there is a smooth asymmetric background due to funnel, and then the enhancement near the zero bias voltage because of the superconductor gap. And then in order to study in detail this enhanced differential conductance, that we divided the spectroscopy by using this funnel. And then this is the result. And then you can see that the very nice data. And the solid line is fitting by using the extended BTK model, where the gap size is around 0.587 milli-electron volt, and then the Z value is around 0.165. Okay, so then we studied this differential conductance from the room temperature, and as you can see, this purple is at 300 Kelvin, and as you can see, is very flat. Well, because it's in the normal state. And then with decreasing temperature around 75 Kelvin, you can see that slight asymmetry. Here, the y-axis is the DIDV normalized by minus 10 millivolt. So minus 10 millivolt, we used it because it's well away from the small gap. So, and then with further decreasing temperature, the asymmetry becomes larger and larger. One thing that I'd like to emphasize is that the asymmetry occurs at temperatures even higher than so-called the coherence temperature, where the condor lattice behavior appears. So in order to analyze this asymmetry, we used a funnel resonance model in condor lattice system, which is proposed by Ifeng. And then here, the differential conductance has two terms. One, G sub 0 is due to background conductance, and this second term is due to the interference term between the C channel and to the F channel. And then, so the figure on the left side, the red solid line is the fitting. In this fitting, we like fixed the parameters, namely the background conductance and the Q1, so the final parameter, and then epsilon 0, which is resonance energy and is a parameter. So I think it's because we fixed it, all these features are like due to some temperature dependent parameters, which explains the asymmetry pretty well. So this is the data at 0 GPa, and then at 1.0 GPa under pressure, similar feature also is observed and well explained by this final resonance model. And then this is all the data set that we obtained, like from ambient pressure all the way to 2.34 GPa. And as mentioned, this final resonance asymmetry exists even at temperature far above transport coherence temperature. That's one feature. And then as also we can see that at temperature higher than the TC, you can see that a deep feature appears, which will be discussed later. And this is the freeing parameters. And then this is point of contact resistance as a function of pressure. And then as you can see, we can, as we can expect that the resistance of the contact resistance is decreased with the increasing pressure, initially sharply decreased, and at pressures higher than 1 GPa is more or less kind of saturated as expected. And then the resonance resonance energy is gradually increases, and then the background conductance and the 1/, contact resistance, they are more or less show similar pattern. Adding gave us some confidence that we are doing the experiment well. So this is the scaling behavior of the asymmetry behavior as a function of reduced temperature, where this reduced temperature is divided by saturation, so-called saturation temperature. And then the asymmetry is evaluated at 10 millivolt. And then this is ambient pressure. And then this is 1 GPa, 1.5, and then those pressures. As you can see, at higher pressures, they all kind of collapse together. And then with the increasing pressure, then deviation temperature is enhanced to 2. So in order to see if this asymmetric, the scaling behavior is due to our like random criterion, we used 60 millivolt criterion and then 2 millivolt criterion. As you can see, these all are pretty much show similar scaling behavior, meaning that at higher temperatures. So then this dashed line is the fitting by using two-fluid scaling model here. And this asymmetry is consists of two terms, namely the effective mass times so-called order parameter, or the fraction of the conduct fluid. And so which explains pretty well. And then instead of this the data, heat versus pressure, here the red is the so-called saturation temperature, where this type of scaling behavior appears. And then this the temperature range is like much higher than 100 Kelvin, which is well above the coherence temperature. And then the figure on the right is the ALPS result by Suyong Zhang et al. And then, as you can see, this 4F weight in the spectrum occurs not below the T coordinates, but well above the coordinate temperature. So we think that this saturation temperature, where the final asymmetric behavior appears, is associated with the itinerancy of the cerium-4 electron. Okay, so then now let's take a look at some of the features that we have not discussed. So this is ambient pressure data, and at 1.5 Kelvin data, then I think we discussed extensively. And then this is 3.0 Kelvin data, which is well above TC. And let me blow it up, this 3.0 Kelvin data, where you can see that there is a slight dip on top of this final asymmetric background. And then when we divided this feature by using the final background, you can see that there is a dip feature, even at temperatures higher than TC. And then this dip feature is suppressed with the increasing temperature. And then one thing that I think that we note is that even though the feature is suppressed, the size of the gap is more or less similar, but the gap is pretty much filled with increasing pressure. That's what we noted. And then this is this normalized the data in the near the TC is 2.0 Kelvin. This feature is due to superconductivity gap, and with increasing pressure, smaller and smaller, and around 2.2 Kelvin, which is close to TC. TC is about 2.28 Kelvin, I think. And then here the feature is become smaller, and then at above TC, you can see that the feature survives. And then at 1.0 GPa, the similar feature appears, like at 2.0 Kelvin, which is still in superconducting state and then suppressed, and at around TC, this enhancement is completely suppressed, and then deep feature still survives. And this feature, I think, is looking at the difference conductance and the temperature dependence seems very similar to the Bisquot 2212 and other Pseudogap features in other classes of superconductors. Okay, so this is the color control plot of these difference conductance, ambient pressure, and then so the temperature range is above TC to emphasize the new feature. And as you can see that the at ambient pressure, this is a Pseudogap-like feature, and then just the gap is pretty much filled. 1.0 GPa, the size of the gap, Pseudogap like is enhanced, large, and still looks like just filling the gap. And then at 1.5 GPa and 2.54 GPa, as you can see that the gap is pretty much filled with increasing pressure. How about magnetic field? So for comparison, I put those two, magnetic field dependence and the temperature dependence. And here, the magnetic field dependence, the temperature is 3.0 Kelvin. As you can see, unlike temperature dependence, where the size of the gap is pretty much constant, on the other hand, the magnetic field dependence, the size of the gap actually is suppressed, like this one. And this is data at 3.0 Kelvin. At 1.0 GPa, similar, right? But the Pseudogap becomes much clearer with the increase in pressure. And then this is the data at increasing higher pressure. Okay, so to summarize our work on the pseudogap feature in serum cobalt 5 under pressure, we successfully performed the quasi-particle scattering spectroscopy of serum cobalt 5 under extreme conditions, and then final resonance is well described by condor-less tunneling mode, and this shows universal scaling under pressure. And the other thing is the pseudogap of serum cobalt 5, as you can see here, the figure on the right side is right panel on the ordinate is 2 delta, is enhanced with the increasing pressure, which is very different from the superconducting gap. I mean, as you can see, the superconducting gap and superconducting TC has a dome, which is a peak around 1.5 GPa. On the other hand, the pseudogap size just increase. And then this clearly shows that the pseudogap feature in serum cobalt 5 is not related to the preformed Kupfer phase or the superconducting state, but rather this is follows the trend of so-called the coherence temperature and the appearance of the serum 5 itineraries, indicating that this pseudogap feature is related to condor hybridization. Then the next question is this a new type of pseudogap that is universal to heavy fermion compound, or just unique to serum cobalt 5? In order to do that, we applied the same technique in the serum rhodium 5, where the maximum temperature is around 2.3 GPa. Because I do not have much time, I'll just quickly run through some of the result. And this is the differential conductance, AFM state, and these features, suppression of AFM state and the appearance of secondary state at 0.3 Kelvin. And then this feature was consistent with the previous report of this phase diagram. And then at 4.8 GPa, which is like this one, and at around 2.0 Kelvin, which is above TC, you can see slight dip. And then with further increasing pressure, then you can see that this very nice dip developed under pressure. So, well, and this work, new result suggests that the pseudogap feature that we observed in serum cobalt 5 is not just for serum cobalt 5, but also appears in serum rhodium 5 too, suggesting that this pseudogap-like behavior in a heavy fermion compound may be universal. So, however, we needed to more work to other compound, not just the serum 1 and 5 system. With that, I'd like to thank you for your attention.
Thank you very much, Professor Park. This is a very nice talk. And we may have time for just maybe a couple of short questions if anybody has any questions. Simao?
Yeah, thanks. It's a very nice talk, Tuson. So, I mean, I guess one remark is that from the orbital selective mode picture, seems to be very reasonable to look for pseudogap. So I think this is an issue may not have had enough attention. So it's great you're looking at that. My question is, do you also have entropy evidence for suppression of denser states?
So in order to do that, I think we needed to be able to measure entropy under pressure, which is non-trivial. And we have some result at low pressure, but at low pressure is not, I think, it's a pseudogap, but I think it's pseudogap-like feature, but it's not really pseudogap, but rather arising from short-range spin-spin correlation. Mm-hmm. At higher pressure side, we have not actually able to do the measure yet. So, but I think it's a good to take a look.
I thought you had entropy data under pressure in one of these 115 materials.
At lower pressure.
Okay.
At lower pressure, but as I mentioned, at lower pressure, is not. I think it's probably due to the onset of short range spin correlation. But at pressure higher than with high pressure, it requires diamond for same role unified. So it's not trivial.
Thank you.
If there's no quick questions, maybe we thank Professor Park again, and then thank you very much for this very nice talk.